Good morning everyone. My name is Prashant. I'm studying in BTech 4th semester CSCC with roll number 22951A05F9. Today my topic is a view to the cloud. What really happens when data is stored on far off servers and distant data centers. Introduction. We live in a world that's awash in information. Awash in information. Way back in 2011, an IBM study estimated that nearly 3 quintillion, that's a 3 with 18 zeros after it, bytes of data were being generated every single day. We are well past that mark now, given the doubling in number of internet users since 2011. The powerful rise of social media and machine learning and the explosive growth in mobile computing, streaming services, and Internet of Things devices. Indeed, according to the latest Cisco Global Cloud Index, some 220,000 quintillion bytes, or if you prefer, 220 zettabytes, or were generated by all people, machine and things in 2016, on track to reach nearly 850 zettabytes in 2021. Much of that is considered ephemeral and so it isn't stored, but even a tiny fraction of the huge number can be impressively large. When it comes to data, Cisco estimates that 1.8 zettabytes are stored in 2016 and that volume will quadruple to 7.2 zettabytes in 2021. Our brains can't really comprehend something as large as zettabyte, but maybe this mental image will help. If each megabyte occupied the space of the period at the end of this sentence, then 1.8 zettabyte would cover about 460 square kilometers, or an area about 8 times the size of Manhattan. Of course, an actual zettabyte of data doesn't occupy any space at all. Data is an abstract concept. Storing data, on the other hand, does take space as well as materials, energy, and sophisticated hardware and software. We need a reliable way to store those many zeros and ones of data so that we can retrieve them later on, whether that's an hour from now or 5 years. And if the information is in some way valuable, whether it's a digitized family history of interest mainly to a small circle of people or a film library of great cultural significance, the data may need to be archived more or less indefinitely. The grand challenge of data storage was hard enough when the rate of accumulation was much lower and nearly all of the data was stored on our own devices. These days, however, we are sending off more to the cloud. That, forgive the pun, needs term for remote data centers operated by likes of Amazon Web Services, Google Cloud Services, IBM Cloud, and Microsoft Azure. Business and governments agencies are increasingly transferring more of their workloads, not just peripheral functions but also mission critical work, to the cloud. Consumers, who make up a growing segment of cloud users, are turning up to the cloud because it allows them to access content and services on any device wherever they go. And yet, despite our growing reliance on the cloud, how many of us have a clear picture of how the cloud operates, or perhaps more important, how our data is stored? Even if it isn't your job to understand such things, the fact remains that your life, in more ways than you probably know, relies on the very basic process of storing zeros and ones. The basics of data storage. First, storing locally on a solid state drive. Step 1. Clicking on the save icon in a program in a computer invokes a firmware that locates where the data is to be stored on the device. Then, storing remotely in the cloud. Step 1. Data is saved locally in the form of the blocks as shown in the picture here. Then step 2. Inside the drive, data is physically located in different blocks. A quick of the flash memory used in solid state drives is that when data is being written, individual bits can only be changed from 1 and 0, never from 0 to 1. So when data is written to a block, all of their bits are first set to 1, erasing any previous data. Then the zeros are written, creating the correct pattern of ones and zeros. Step 3. Another quirk of flash memory is that it's prone to corrupting stored bits, and this corruption tends to affect clusters of bits that are located close together. Error correcting codes can compensate for any of certain numbers of corrupted bits per byte. So each bit in the byte of data is stored in different block to minimize the likelihood of multiple bits in a given byte being corrupted. Step 4. Because erasing a block is slow, each time a portion of data on a block is updated, the updated data is written to an empty part of the block, if possible, and the original data is marked as invalid. Eventually, though, the block must be erased to allow new data to be written to it. Then, step 2 for cloud. Step 2. Data is transmitted over the internet to a data center. Step 3. For redundancy, data is stored on at least two hardware disks or two solid state drives, which may not be in the same data center, following the same basic method described above for local storage. Step 4. Later, the data center follows best practices. The data is backed onto magnetic tape. However, not all data centers use tape backup. Then open. Reading back stored data. Reading back data always introduces errors, but correcting errors can locate the errors in a block and correct them, provided that the block has only one or two errors. If the block has multiple errors, the software can't correct them, and the block is deemed unreadable. Errors tend to occur in bursts and may be caused by stray electromagnetic fields. For example, a phone ringing or a motor turning on. Errors also arise from imperfections in the storage medium. A deeper dive into the cloud. Though most data of that gets stored is still retained locally, a growing number of people and devices are sending an even greater share of their data to remote data centers. Cloud security. Cloud data centers protect data using encryption and firewalls. Okay. Most centers offer multiple layers of each. Opting for the highest level of encryption and firewall protection will, of course, increase the amount of time it takes to store and retrieve the data. Three basic types of cloud storage are hard disk drives, solid state drives, and magnetic tape cartridges. The cloud data center is basically a warehouse for data with multiple racks of specialized storage computers called database servers. Data from multiple servers moves over the internet to a cloud data server, which is connected to the outside world via optical fiber or, in some cases, satellite gigabit per second links. One particular magnetic recording allows for data densities of about 3 gigabytes per square millimeter. Magnetic storage was a solid state. Hard disk drives and magnetic tape stored data by magnetizing particles that go to the surfaces. The amount of data that can be stored in a given space, the density that is a function of the size of smallest magnetized area that the recording head can create. Perpendicular recording can store about 3 gigabits per square millimeter. Newer drives based on heat assisted magnetic recording and microwave assisted magnetic recording boast even higher densities. Flash memory in solid state drive uses a single transistor for each bit. Data centers are replacing HDDs with SSDs, which cost 4 or 5 times as much but are several orders of magnitude faster. On the outside, a solid state drive may look similar to HDD, but inside you'll find a printed circuit board studded with flash memory chips. Conclusion. Local versus storage, cloud storage. Lunt explains the basic principles of cloud storage, contrasting local storage on solid state drives, SSDs, with cloud storage in remote data centers. Local storage involves saving data on physical drives within devices, which offers quick access times but limited capability and susceptibility to data loss due to hardware facilities. hardware failures. On the other hand, cloud storage involves transmitting data over the internet to remote data centers equipped with extensive storage capabilities. These centers utilize redundant storage methods such as saving data on multiple hard drives or SSDs across different locations to ensure data integrity and availability. Technological advancements in storage media. The article delves into the technological advancements that have been enabled the current capabilities of data storage. Perpendicular magnetic recording (PMR) allows for higher data densities on HDDs, while heat-resistant magnetic recording and microwave-assisted magnetic recording promise even greater densities. SSDs, which use flash memory, offer significantly faster access times compared to HDD. However, HDDs are prone to data corruption due to the nature of flash memory necessitating the sophisticated error correcting codes to maintain data integrity. Magnetic tape, although slower in access times, provides higher data persistence and used for long-term data archiving. Cloud data centers are a modern problem. The transition to cloud data centers is driven by their ability to handle vast amounts of data efficiently. These centers operate as a large warehouse filled with specialized storage computers known as database servers. Data from multiple users is transmitted to these centers via high-speed optical fiber or satellite links. Cloud data center provide redundancy, ensuring that cloud is stored on multiple devices, often in different locations to prevent data loss. Moreover, best practices in data center include regular backups onto magnetic tapes for additional security. Security and redundancy. Security is a paramount concern in cloud data storage. Cloud data centers employ multiple layers of encryption and firewall protection to safeguard data. The highest levels of security increase the time required for data storage and retrieval, but they are essential for protecting sensitive information. Redundancy in cloud storage ensures that even if one storage device fails, the data remains accessible from another device. This redundancy is crucial for both businesses and consumers who rely on uninterrupted access to the data. The implications for business and consumers. Business and government agencies increasingly rely on cloud storage for not only peripheral functions but also mission critical operations. The scalability and flexibility of cloud storage allows these entities to manage their data efficiently without the need for extensive on-site infrastructure. For consumers, cloud storage offers the convenience of accessing content and services from any device anywhere. Thus, accessibility has made cloud storage as an integral part of daily life, underpinning everything from personal photo archives to professional document management systems. The future of cloud storage. Looking ahead, the article suggests that the future of cloud storage will be shaped by continued advancements in storage technologies and the growing need for efficient data management solutions. The increasing volume of data generated by IoT devices, autonomous vehicles, and other emerging technologies will drive demand for more sophisticated storage solutions. Innovations in data compression, faster data transmission methods, and enhanced error correction techniques will be crucial in meeting this demand. In conclusion, a view to the cloud provides a comprehensive overview of the challenges and innovations in cloud data storage. The transition shift in how data is managed, offering numerous benefits in terms of capacity, security, and accessibility. As data generation continues to accelerate, the importance of reliable and efficient storage solutions will only grow, making advancement in the field critical for both business and consumers alike. Thank you.